portions of the pattern can be extracted. Say, for example, this smaller unit here, a rectangle, or more of a square unit here, or even a smaller unit here, which is a mathematical representation of the whole pattern of atoms in this lattice. And so the smallest unit that is representative of the whole structure is what we term the unit cell. And so again, just stating that clearly, the unit cell, it's the simplest repeating unit that is representative of the extended structure in 3 dimensions this time. The packed atoms in the smallest repeating volume can contain information about the complete structure of that crystal. So a crystal, therefore, is a regular array of packed atoms or ions that are described by a unit cell. You can see here in this cubic unit cell that the edge lengths are all about the same, and that the angles within that each edge length makes are about the same, and that we can see portions of atoms that are in the unit cell. So that is, not whole atoms exist in the unit cell, but pieces of them, and we need to account for that in some of our calculations for atoms per unit volume per unit cell. So this unit cell shown here is actually what we'll see and call a body-centered cubic unit cell. And of course, a mathematical multiplication of it on top of itself, to the front, to the back, to the left, to the right, and down below in all 3 dimensions describes the larger structure as a whole for this packed array of atoms or ions. If you consider some of the ideas we already had about edge lengths, say for example A, B, and C, and the angles with which they meet each other, alpha, beta, and gamma, they need not necessarily be the same, and so there are permutations of this. So if you were to permutate all those options, say for example, where all edge lengths are the same, A equals B equals C, we define a cube, of course. That also means that the angles must be 90 degrees, alpha, beta, gamma equal 90 degrees. And as we permutate through all the options where not all those lengths are equivalent, so here A and B may be the same, but not the same as C, we establish a different type of crystal structure, provided that the angles are still the same. So alpha, beta, gamma all equal 90 still, but we've just allowed one edge length to differ, and we've created now the tetragonal unit cell option. And by varying all the edge length options and angle options, we create the other 5 unit cell systems or crystal systems: orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Okay, so putting a little bit more structure to it now. Here we have the cubic systems. We knew that would be all edge lengths the same. So here, abbreviated with edge length A, and the angles are all, of course, 90. We put a picture to the idea that one edge length is now going to be different. So that is, we allow C to exist as being different in dimensions than the other 2 edges, but all angles are still 90 degrees. We've generated tetragonal unit cell geometry, and now allowing all edge lengths to be different, we have A, B, and C here, all still meeting at 90 degrees to one another, and we've created the orthorhombic system. The other variants are shown here: rhombohedral, hexagonal, monoclinic, and triclinic. We'll spend a little bit more time on the hexagonal system later in this video. Okay, so those were just simple unit cells, and we haven't yet fully settled on all the options for putting atoms into those representative units for the whole crystal from a crystal of matter. And so the simple cubic lattice is a good place to start, and that it might have been a good place where you were thinking of going as well, where we would now locate atoms at the corners of this cube. And so, as you know, there are 8 corners to a cube, and so we're going to place 8 atoms at each of those sites. And so as we do that, you can think about the sort of features here now being atoms. And of course, to fill space properly and to think about stabilizing the material, say in a metal, we would pack those densely and have the sea of electrons bond everything together, as we recall for metallic bonding. So what that means is that these spheres actually end up touching throughout different directions and angles throughout the unit cell. In the simple unit cell, you can see that they meet at the middle of an edge, and each sphere touches at the neighboring sites here. So these two front spheres, of course, contact at the midway point of one of those edges, and likewise along the other edge. Okay, so with that, we can see here that there would be 8 atoms in this unit cell, and nothing in the middle, and nothing located at the faces, say shown here, 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 in the back, and on the bottom as well. So on those 6 faces, there are no centered atoms there. So that simple cubic structure, it's actually very rare, and very few examples can be found. One is the polonium metal, and it's the only one that can be found under standard temperature and pressure conditions where a metal can occupy that lattice type. So polonium exists with at room temperature and pressure with a simple cubic structure. And based on where the contact points are, we can define the close packed directions. So close packing requires that atoms contact along that direction. So close packing directions are, of course, the cube edges, as we saw in the previous slide. Okay, so these atoms here are contacting along that cube edge. So that would be the close packed direction. Okay, let's recall what we understand about the coordination number. So coordination number, of course, is defined as the number of similar atoms or ions which surround any particular atom or ion. So we might ask, what is the coordination number of polonium in this lattice? And this is a bit difficult to consider when we only look at the unit cell, because we have to think past that to fully understand the number of nearest neighbors around each atom in the lattice. So take a minute to think about that, and provide your answer once you've had a chance. If you need to, pause the video and provide your answer when ready. Okay, so hopefully you were thinking about, say, for example, this sphere here, contacting neighbor there and a neighbor there. So those 2 neighbors are easy to think about. Of course, one over into the next unit cell, and then one down into the next unit cell. So it looks like we've got 4 so far. And then because we know we contact in 3 dimensions, so the next unit cell coming out of the page, there would be a sphere to contact. So that would be a 5th. And then, of course, there's the one right behind it, which we can just kind of see in here. So that would be our 6th contact point. So the coordination number for polonium would be 6. Okay, let's just clean that up so that you've got that shown a little bit easier. Another way to see that more clearly here is in this diagram here, where we've allowed several unit cells to stack up next to each other, and you can see that central polonium atom, for example, has 6 nearest neighbors, each contacting along the close packed directions of those unit cells. Okay, another idea is the atomic packing factor, so the APF, also abbreviated. It's defined as the volume of atoms in that unit cell divided by the volume of the unit cell. So with the simple geometric analysis that we have here of putting spheres into 3D space established by a cube, of course we cannot fill all space because at some point these spheres, which are modeled as, say, hard spheres, will contact and will leave void space. So we could try to estimate or calculate the atomic factor for many systems, including our simple cubic system. So take a minute to consider this. See if you can devise an equation here to help us. So we first need to know and count the number of spheres in this volume. And then if we use the equation for a sphere and the volume of a sphere, we'd be able to determine the numerator if we knew the number of spheres and the volume of them. And then we'd be able to divide through by the volume of the unit cell. In this case, we've been given the edge length A, and we know that all edges are the same because we were in the cubic system. So the volume is simply of the unit cell is, of course, going to be A cubed. So use those ideas and see if you can calculate the atomic packing factor for polonium without even being given the radius of the atom. Pause the video if you need. Okay, so a moment ago we said that the denominator was the easy piece of this equation, where we knew the volume of the unit cell, of course, is going to be A cubed. Now we're trying to get to the answer, actually, in a numerical format. It'll be unitless, and so we need the numerator to eliminate the A's in the denominator. So we want to provide the volume due to atoms in the unit cell based on the value A. And so we knew that there were 8 atoms located at each of the corners of the atom. So here I'll just put little features here to represent those 8. One is going to be in the back of the page, and I think I'll keep our diagram clean, but we can see one would be in the back, so I haven't drawn that 8th one. And if you inspect the shape of the atoms that are cut away from whole spheres, you can see that each corner only has 1/8 of an atom. And so with 8 corners, this tells us that we have 1 atom in total per unit cell. And that's going to help us with the numerator. Of course, these atoms are spheres, so we simply need to know the volume of a sphere. And so the volume of a sphere is, of course, 4/3 pi r cubed, where r is the radius of that sphere. And so if we can express r in terms of the edge length, we'll be in better shape for eliminating the A in the denominator above. Well, it follows here from our diagram that if A is defined as the distance between the center of 2 atoms, and that they contact at the midpoint, and we know that A equals 2r, and therefore r equals 1/2 of A. And so we can substitute this into the simple equation and help us get to the answer. And so the numerator here, of course, would be the number of spheres in this unit cell. So that is, for my first piece, 1 sphere, 1 atom. And now we want the numerator. So it's going to be 4/3 pi and then 1/2 A all cubed. You can see here that we're already set up to cancel A units. Okay, so simplifying this, we will get 4/3 pi. A to the power 3 cancels a to the power 3, and we are left with a half to the power of 3. And if you complete the calculation, you'll find that the atomic packing factor here is 0.52. Okay, so the simple cubic cell has only filled space with about 52% efficiency, if you consider it that way. Again, a value here that speaks to the reason why polonium is one of the only options here for establishing the simple cubic structure, in that asking metals to pack space this way is very inefficient. Again, only 52% of the space is filled.